All right, it's time to go over this worksheet. So I'm just going to be going through each section. I'm going to do a few problems from each section. Hopefully I hit all the different types, and you can ask questions in the video if you have any. So let's look at number one. When we're evaluating a log, the idea here is what power do I need to raise 3 to give me 27? So that means I need to rewrite this 27 as an exponent, 3 to something power. So log 3, 27 happens to be 3 to the third. These are inverses of each other, so they reduce, and I'm left with 3, which is going to be my answer. Let's look at number 4. So how do I rewrite this 1 over 36 as 6 to some exponent? So we can start with this 36. That turns into 1 over 6 squared. Now I can move that to the top because I need to move, it needs to be 6 to some exponent. So that becomes 6 to the negative 2. That comes and reduces, and then I get negative 2. Let's look at number 10. So log base 36, fourth root of 36. So whenever you have a root, that goes in the denominator of your exponent. So this is going to become log base 36 of 36, since this is to the first power, so 1 over whatever your root is going to be 4. These are inverses, so they reduce, and I get 1 over 4. Number 16. Log e to the ln 100. E and ln, they are inverses because ln is log base e, so those reduce. So you get log 100. Remember, log is log base 10, so that's going to be, how do I rewrite 100 as 10 to some exponent? So that's going to be 10 squared. Those cancel out because they're inverses, and so you're left with 2. Let's look at 21. You get log 1/6 of 216. So how do I rewrite this? Well, whenever you get a fraction as your base in the log, if you do the reciprocal of it, so move the 6 to the top, so that becomes log base 6, I can then add a negative to the front here. Just makes it a little easier for us. And so that's going to be 216. Well, I can rewrite the 216 as 6 to the third. Those are inverses, so you get the negative and then 3. Now sometimes on number 24, I get log base 8 of 16. Sometimes it's literally impossible for us to rewrite that base to make them the same. So how do I rewrite 16 as 8? 2 squared? No. 2 to the, well, it's not 8, so 8 to the first, no. 8 squared is 64. Yeah, I don't know. So what we do is we set it equal to a number I don't know, so we say x. Then we convert it into an exponent. So I'm going to say base 8 to both sides. So those are going to reduce, so you get 16 equals 8 to the x. Now this becomes 8 to the log base 8 exponent. That's why they're inverses and they cancel out. And this becomes 8 to the x power. Now I just need to figure out what base can I make both of those into. 2 to the something power, 3 to the something power, 4 to the something power, 5 to the something power. What base can I make these into to where the bases are the same? And so it happens to be 2. So I can make this into 2 to the fourth. And then the 8 becomes 2 to the third. And then whatever that is there, you just multiply it. Now that the bases are the same, you can set the exponents equal to each other, divide both sides by 3, and you get 4/3. Now you cannot include x in your answer. I can't say x equals this because x was not in the original problem. So we just have to be a little careful of that. So now let's find some inverses. So let's look at number 26. So I have 3 to the x plus 3 minus 1. And that's y equals. So we switch the x and y. Now I just need to get y by itself. So we need to isolate this term. So add 1 to both sides. Now the inverse of that base 3, right? It says 3 to the y plus 3 power. The inverse of that base 3 is log base 3. So we're going to take log base 3 to both sides. So we're going to get log 3 of x plus 1 equals, well, those are inverses, so they cancel out, and we get y plus 3. Now I can subtract 3 on both sides, and so I get log base 3 of x plus 1 minus 3 equals my y. That is my inverse. Now to verify, that means I should take this and plug it in for x. So, and let's see, does it reduce down into x? So I get 3 to the log base 3 of x plus 1 minus 3 plus 3 minus 1. Well, the negative 3 and plus 3 cancel out. Then the log base 3 and the 3 cancel out. And then the 1 and the negative 1 cancel out, and you're left with x. So therefore, they are inverses of each other. Now for this next one, I'm just going to kind of set us up for it. So number 27, switch the x and y. So you're going to get x equals log base 2 of y plus 5 plus 6. So isolate the log, so minus the 6. And then the inverse to log base 2 is base 2. So you take base 2 to both sides. Minus 5 on both sides. And that's going to equal my y. Once again, to test it, if you plug that back in for x, right, I switched the x and y already, but if you plug that back in for x, watch them unfold, and that's how we find what the inverse is, or if they're inverses of each other. Number 28, switch the x and y, add 1. Now, y is in the denominator. To get it out of the denominator, you multiply. I didn't have room, so I wrote it up there. So now I need to isolate and get y by itself while it's being multiplied by that x plus 1, so I can divide both sides by x plus 1. Minus 3. So you get y equals 3 over x plus 1 minus 3. And that's going to be my value. That is the inverse. All right, let's look at number 36. So the first one is an absolute value. So the parent graph, it has a horizontal shift to -2, so I'm going to shift it over 2 spaces. And then its absolute value. So it's going to go up 1 over 1 like that. And it's a solid line. And so there's my absolute value graph. Now, because it's an inequality, that means that the region that's shaded represents the solutions. So to test that, I need to plug in a value and see if it's true or false. So let's say if I plug in 0, 0. So the question is 0 less than or equal to 0 plus 2? Is that true or false? That is true. So we're going to say shade the side that's true. So it's true on this side, so I'm going to shade that side. Now let's graph the next one. It's going to move over +2. It's going to move up 3. 1, 2, 3. And then it's going to go down. Now, when it comes to these graphs, it's a good idea to draw them fairly accurately. So plug in values. So for example, even though this is my starting point, if I plugged in 1, you're going to get 2. If I plugged in 0, you're going to get -1. So do your best to kind of draw them at least a little accurately here. And then it's a dotted line. Wow, this computer did a terrible job trying to draw it dotted. There you go. That looks really bad. So it's dotted. So now, once again, I need to test to see if it's going to be true or false. Well, it looks like it's too close to 0, 0. So I'm not going to try 0, 0. Maybe I'm going to try, let's try this one right here, which is 2, 0. So I'm going to plug in 0 for y, plug in 2 for x. So is 0 greater than, let's see, 2 minus 2 is 0, negative 2 is 0, so 0 plus 3. That is false. So this side is false, which makes the other side true. And so wherever the region overlaps is the solution. So since it overlaps here, this is what the solution is going to be. So the purple, and notice I'm trying to darken it as best as I can. That's what you need to do. You need to make sure that that's darkened really, really well to indicate that that's going to be the solution. So the point here is you're going to graph, then shade, graph, then shade. You could have an unlimited amount of graphs, which means for every graph that you have, you're going to shade. Wherever the intersections overlap, that's going to be your solution. Let's look at number 40. So the first one, it says y is less than 2. That's a horizontal line at 2. It's solid. And then it's less than that, so that's everything below it. So I'll shade here. Then the next one is a line, 2 minus x, so it starts at 2, but it has a, so it starts here at 2, but it's a slope of negative 1, so down 1 over 1, down 1 over 1, and it's dotted. I know this doesn't do a very good job. Maybe I'll try dash. See, it doesn't do a very good job with that. But it's dashed, so pick 0, 0, or any other value, just not on the line. I like 0, 0 because it seems easier. So if I plug in 0, 0, I get 0 is greater than 2 minus 0. That is false. So since this is false, this side is what's true. And so that's the true. And then now the last one. Here, I'm going to draft this in black, so it's easier to see. That's supposed to be dotted. And then the last one, y is greater than x minus 2. So now it starts at negative 2, and it has a positive slope. So up 1 over 1, up 1 over 1, up 1 over 1. And once again, it's not solid. It's dashed. So once again, we pick a value, 0, 0. Is 0 greater than 0 minus 2? Is 0 greater than negative 2? That is true. So this is the side that's true. Now wherever they overlap, that's going to be the answer, and we have to darken that, and that's going to be this little wedge right here. Now don't assume that it's always going to be like whatever's in between all the graphs. Do not assume that. It just happens to be this graph in which they all overlap. All right, let's graph logarithms. So this first one's going to be 43. So with the logarithm, the parent graph starts at 1, 0, has a horizontal asymptote here, and it has this shape. So I have a horizontal shift to negative 2, and it's going to move down 1. So from here, it's going to move over 2 and down 1. So there's my starting value. Now we should also draw in the asymptote. So the asymptote also shifts over 2 spaces. So then now I can draw my graph as it goes along it. And that's it. Now if I wanted to find the domain here would be from, well, starts at the horizontal asymptote, so negative 2, and it goes on to infinity. And then the range, that's negative infinity to positive infinity. It might be a good idea to, on these, even though I didn't indicate it, let's practice finding the domain and range on these. It'll be a good idea. Now let's look at 45. Now because of 45, it says log base 1/4. we need to recognize that I should do the reciprocal of that, so that becomes log base 4, but then the negative goes in front. Now that I know that there's a negative in front, that means it's going to be a reflection over the x-axis. So starting from my starting value, it's going to shift over 2 and down 1. So from here, it's going to shift over 2 and down 1. My horizontal asymptote is also going to move over 2 spaces, but now it has that reflection. So it's going to do like that. Kind of like as if the graph flipped. All right, so writing the equation in graphing form. So at first, because it uses the word vertex, I need to think, okay, that means it's a parabola. So the graphing form for parabola is y equals a times x minus h squared plus k. Now the vertex is your h and k. So this is -2, and this is 1. So I get a times x plus 2 squared plus 1. Now the passing through the origin, that tells you what your x and y is, because we still need to find a. I don't know what a is. So when I use that other point, that gives me a value for x and y. So now the only variable is a, and then I just solve for a. So if I plug in what the origin is, so 0, this becomes 0 equals a times 4 plus 1. Subtract 1. Divide by 4. So a is -1/4. So your answer is going to be y equals -1/4 times x plus 2 squared plus 1. So you just leave your x and y as their variables, but you plug in for h and k. And you do that every single time. Nothing changes for the problem. In these problems here, I gave you points. So instead of plugging 0, 0, you plug in the points. All right. So now, ooh, look at this typo. That is definitely not 80. All right, so let's take a look at a few of these. Now, when we're graphing an inequality, if you notice, there's only one variable, only x. So that means the graphical representation is a number line, which means our actual answer is going to be in interval notation in some fashion. It could be in any shape, right? It could be represented in multiple ways. But the idea is I need to find where it intersects those boundary points. I need to know those boundary points. So we find the number line, we find the boundary points so we can put them on the number lines, and we test true or false to see where we need to shade. The true area represents our solution. So let's look at 58. So we pretend it's an equal sign. So solving an inequality, you break it into two equations. One positive and one negative. So now I solve for x. So add 5, divide by 3. For this one, subtract 5, divide by 3. So those are our two boundary points. So now we need to put them on a number line. 1/3 and 3. It says equal to, so we represent that with closed circle. Now I need to know where I need to shade. I don't know where to shade yet. So we have to test to see if it's true or false. So if I plug in 0, I want to see is that true or false. So if I plug in 0 for x, I get 5 is less than or equal to 4. That is false. Now I know you're like, wait a minute, what? How is that 5? You just simplify it. And I'm going to go kind of quick on these because I'm assuming we know how to plug things in and just being able to simplify. But if I plugged in 0, 3 times 0 is 0. 0 minus 5 is -5. The absolute value of -5 is 5. So 5 less than or equal to 4. If I plug in 2, that gives me 1 is less than or equal to 4. That's true. If I plug in 4, That's going to give me 12 minus 5. That's 7. That gives me 7 is less than or equal to 4. That's false. So the true value, that's my graphical representation. But I want to write this in interval notation. So that's my answer here. Negative 1/3 to third. Now, it does not matter what type of equation it is. You still follow the example or the idea, find the boundary points. Once you find the boundary points, test true or false. The difference is the type of equation tells you how you need to solve it. So for example, let's look at 65. So I have x is greater than x squared. Well, it's quadratic. So set it equal to 0. So I have minus x on both sides. Pretend it's an equal sign. Well, I could use the quadratic formula. I could factor it. Right? There's an x in common, GCF, and I factor out that x. So that means x equals 0 and x equals 1 if I set each one equal to 0. These are my boundary points. I'm doing the same thing. The difference, it's a quadratic equation, so you solve it with quadratic methods. So I have 0 and 1, and now I need to test true or false. So if I plug in negative 1, and it's open circle for these. So if I plug in negative 1, I get negative 1 is greater than 1. That is false. If I plug in 1/2, I get 1/2 is greater than 1/4, because 1/2 squared is 1/4. That's true. If I plug in 2, I get 2 is greater than 4. That is false. So this right here is my solution set. So it's 0 to 1. And that is my answer. So even though they're different types, we have quadratic, absolute value, we're basically doing the same thing. Every single absolute value, you're going to break it up into two equations. One positive, one negative, and solve for there. For every quadratic that you see, you can try factoring it. You could try using the quadratic formula. We just need to find the boundary points. Now, let's look at number 61, and we'll close with this one. I have x squared plus 1 is less than 0. Okay, well, pretend it's an equal sign. Now, in solving this, you guys are going to get i's. Well, i's mean that there's no value on the number line. So your number line has no boundary points, which means you can test any value on the number line. It doesn't matter which value. It's just think of it as one giant region. Instead of having the boundary points breaking into multiple regions, we just have one giant region. And so, since it's one giant boundary point, if I plug in any value, let's say 0, I get 0 squared plus 1. Is that less than 0? So is 1 less than 0? That's false. That means the entire thing is false. No solution. And the reason why this is no solution is because there's no value for x that I can pick that's going to make it less than 0. There are none. Another way of thinking about it, this is my graph, moves up 1, and it's a parabola. Is there any values below the x-axis? Are there any values that are less than 0? The answer is no, which is why it's no solution.